Okay, this section is a little more straightforward. We are defining one new thing about vectors. It's the dot product. We're multiplying. There's another way to multiply vectors, but we won't get to that in this class. U dot v is magnitude of u, magnitude of v, cosine of theta, where theta is the angle between u and v. And another way to do u dot v, which is actually the way we compute it most often, is u1 v1 plus u2 v2. That is the x component of u1 times the x component of v1, or of v, and the x component, or sorry, the y component of u times the y component of v. It's really pretty straightforward, as seen on question number 1, which gives you a vector like v is 7i minus 3j, and w is negative 4i minus j, and they want us to dot those. I prefer to write these in this form. And then to dot them, what I do is I multiply these, and then add, multiply these, and I arrive at an answer. Note, this is a number answer, also called a scalar, not a vector. So a dot product is a scalar value. It's not a vector value. Okay, so question 1, question 2, those both go along with that. Question 3 gives us two vectors. And asks us to find the angle between them. Well, we can use our first form of the dot product to do that. So that means, if you take that first form and rewrite it, that the cosine of theta is u dot v over magnitude of u, magnitude of v. Which means the cosine of theta, if I want theta, I would take the cosine inverse of this answer over here. So, that's not terribly difficult. U dot v, or in my case v dot w, is going to be negative 20 plus 96, which is negative 76. Sorry, positive 76. Magnitude of our first vector, here it says u, but again we're using v right here, would be the square root of 25 plus 64, which is 99. And then our second vector would be the square root of 16 plus 144, that's the square root of 160. And just a little quick math here. That's the square root of 15,840. And I don't need to work on simplifying that too much because I just need to get an inverse cosine of that answer. So I'll just plug that in the calculator, get an inverse cosine. Life's good. Okay, good enough. Let's move along. Question 5 is the same. Question 4 is the same. Question 5 asks you to determine whether two vectors are orthogonal. So they give me vector v is 6i plus 19j, and they give me vector w is 3i minus j. Well, here's the thing that you do to determine if vectors are orthogonal or not. It goes back to here. Cosine of theta is this. So if that's going to be 0, this is not going to be 0 down here, which is good, unless you had 0 magnitude vectors. Well, that would mean you didn't have a vector, you just had a dot, right? Because that would mean you had no length. So basically, this is going to be 0 if u dot v is 0. Well, if the cosine is 0, then you're looking at a 90-degree angle between your vectors, which means they're orthogonal. Or perpendicular is a word we used in geometry, but we like orthogonal for vectors. So we're basically trying to find out if the dot product is 0 or not. So just dot them. 18 minus 19 is negative 1. That's not 0. These are not orthogonal. So that's pretty straightforward for number 5. Then the last questions that you have go one more step. And they give you a series, well, they give you 2 vectors, and ask you to determine if they are orthogonal, parallel, or neither. Well, you could test if these are orthogonal. You could dot them. You would get 50 plus 32 is 82. These are not orthogonal. Are they parallel? Well, the way you check they're parallel is basically you see if they're going in the same direction or not. You could reduce them down to one unit vector and see if they're the same unit vector, but really if you just look, are these multiplied by the same amount? Oh, multiplied by 2, multiplied by 2, I get this vector down here. This vector is going the same way as that one, it's just twice as long. So, yes, these are parallel. If one was neither, then these numbers wouldn't match up, and the dot product wouldn't be 0, and you would know that it's neither one of these parallel or orthogonal. I think you are totally prepared to knock out this homework now.